In the past century, our planet has been whispering into the cosmos, sometimes on purpose, mostly by accident. Could something out there have heard us and answered in a way we didn't expect? Tonight, a calm journey through what we know, what we don't, and a careful hypothesis. If an object called 3I/ATLAS ever appeared as a reply, what would science require for us to take that idea seriously? Chapter 1. Shouting into the dark. This chapter previews how Earth began broadcasting to the universe, the difference between listening and transmitting, and why radio became our first cosmic language. For more than 100 years, Earth has been leaking radio waves into space. Early long-wave experiments, commercial AM broadcasts, and later television carriers all slipped through our atmosphere at the speed of light. According to the SETI Institute, these unintentional emissions create a rough sphere of detectability centered on Earth, our so-called radio bubble. It isn't a perfect sphere, and it isn't uniformly bright. Powerful radars briefly outshine the rest, while consumer broadcasts fade quickly with distance due to the inverse square law, which says a signal's strength drops with the square of the distance. In the 1970s, we also tried deliberate hellos. NASA's Pioneer 10 and 11 carried plaques designed by Carl Sagan, Linda Salzman Sagan, and Frank Drake, showing human figures, the hydrogen spin-flip transition as a time standard, and a map of pulsars to triangulate the sun's position. Voyager 1 and 2 followed with the golden record, described by NASA as a time capsule of images, sounds, and greetings. And in 1974, the Arecibo Observatory sent a brief, symbolic message toward the globular cluster M13. As the observatory staff have explained in public talks, it was never intended as a practical contact attempt. M13 is about 25,000 light-years away, but it demonstrated how to structure a message. 1,679 bits, arranged as 23 by 73, both prime numbers, encoding basic math, chemistry, DNA, a person, and the solar system. Radio was chosen for good reasons. As Giuseppe Cocconi and Philip Morrison argued in Nature in 1959, the radio part of the spectrum, especially near 1,420 megahertz, the natural emission frequency of neutral hydrogen, is quiet and universal. Hydrogen is everywhere. The water hole between hydrogen and hydroxyl lines is a natural radio haven where a civilization might look and listen. Yet, much of our leakage is faint. As researchers at the SETI Institute and Breakthrough Listen have often noted, ordinary TV and FM signals disperse into noise a few light-years out. The brightest human transmitters are planetary radars like Arecibo's former S-band system, NASA's Goldstone Solar System radar in California, and ESA's radar experiments, which briefly turn Earth into a lighthouse. Meanwhile, the Deep Space Network, NASA's global trio of dishes near Goldstone, Madrid, and Canberra, keeps contact with distant spacecraft. To a hypothetical radio astronomer elsewhere, Earth would present a peculiar, structured spectrum. Narrow carriers that rise and fall with our planet's rotation and occasional high-power radar sweeps. So far, we've learned that Earth's radio voice has two parts: faint, accidental chatter, and rare, powerful beacons. How do you balance the urge to listen with the temptation to speak? That question split the community into two traditions. According to the SETI Institute, passive SETI focuses on listening, surveying millions of stars, combing for narrowband tones or patterns that nature rarely produces. Active SETI, sometimes called METI, messaging extraterrestrial intelligence, proposes deliberate transmissions. MEDI International has argued publicly that the galaxy may be full of listeners and that someone must speak first. Others, including many at the International Academy of Astronautics, advise caution. Once you announce yourself loudly, you cannot recall your voice. There are also cautionary stories. In 1967, Jocelyn Bell Burnell and Anthony Hewish detected a remarkably regular radio pulse. For a moment, the team considered LGM-1, Little Green Men. As Cambridge and later global work showed, it was the first pulsar, a neutron star's lighthouse beam. In 1977, the Big Ear Radio Observatory registered the WOW signal, 72 seconds near the hydrogen line. Jerry Amon's handwritten "wow" in the margin became legend. But it never repeated. And mainstream consensus today is that the WOW signal remains unexplained, not confirmed as extraterrestrial. These examples shape SETI's protocols. Replicate first, verify with multiple telescopes, rule out earthly interference, and only then inform the world. At the policy level, the United Nations Committee on the Peaceful Uses of Outer Space, the International Telecommunication Union, and scientific bodies like COASPAR all have roles in space governance, spectrum protection, and planetary protection. None officially define who speaks for Earth. But according to publicly available statements, they have discussed principles that would guide post-detection behavior. The Rio scale, developed by researchers in the SETI community, even offers a way to classify announcements by significance and credibility. What happens when our quiet listening suddenly meets a new kind of visitor, one not born in our solar system? And if it did, how would we know what it meant? Chapter 2. The First Interstellar Visitors. This chapter previews what astronomers learned from 1I/Oumuamua and 2I/Borisov, and why those lessons set the yardstick for any claim about a third visitor. In 2017, the Pan-STARRS survey in Hawaii flagged a fast, dim object on a hyperbolic path, unbound to the sun. The International Astronomical Union designated it 1I/Oumuamua, meaning scout in Hawaiian. According to NASA and peer-reviewed studies, it was small, likely tens to perhaps hundreds of meters long, showed no obvious coma, and displayed non-gravitational acceleration. Tiny but real departures from a pure Keplerian trajectory. The mainstream consensus today is that natural mechanisms are plausible. Outgassing of volatiles that didn't produce a visible coma, sublimation of unusual ices, or other thermal effects could produce a gentle rocket push. Some researchers have explored alternative hypotheses, including radiation pressure effects on a thin object or exotic ices. But the center of gravity in the literature still leans toward natural explanations, pending conclusive data. In 2019, 2I/Borisov appeared, clearly a comet, with a coma and tail. As ESA and numerous observatories reported, its composition looked broadly similar to solar system comets, which reassured astronomers that interstellar comets exist and can resemble our own. So far, we've learned that interstellar doesn't automatically mean artificial. Oumuamua was odd, yet plausibly natural. Borisov was normal. Those two objects set the baseline. A new 3I would have to pass strict tests, a measured hyperbolic eccentricity, consistent astrometry across multiple instruments, careful removal of biases, and if claims of artificial features arose, extraordinary evidence. Which raises a careful, sleep-friendly question. If a future object appeared with properties that seem to answer our radio life story, what would the scientific path to that conclusion actually look like? Chapter 3. the 3I/ATLAS hypothesis. This chapter previews a thought experiment. If a third interstellar object, nicknamed 3I/ATLAS, were ever reported, and if it behaved strangely, what sequence of observations and verifications would scientists require? Before we go further, a clear statement. As of the time of this recording, the only interstellar objects confirmed by the IAU are 1I/Oumuamua and 2I/Borisov. Everything you are about to hear about 3I/ATLAS is presented as a hypothesis, a careful thought experiment about how science would proceed if such a discovery were claimed. In our scenario, an all-sky survey similar in spirit to ATLAS, the Asteroid Terrestrial Impact Last Alert System, flags a fast mover on a hyperbolic path. Confirmation arrives from independent facilities, Pan-STARRS, the Zwicky Transient Facility, and professional follow-ups worldwide. The Minor Planet Center posts preliminary elements indicating an eccentricity above 1, the mathematical signature of an object not bound to the Sun. Astrometric certainty would come first. According to MPC practices, observers around the globe would contribute positions to refine the orbit. Errors from timing, plate solutions, and atmosphere would be quantified. Only after a robust orbit would astronomers suggest an I designation. Photometry would follow. Surveys and large telescopes would measure the light curve, the brightness variations as the object rotates, to infer shape and rotation period. If the curve showed regular, stable modulation rather than chaotic tumbling, that would be unusual and interesting, but not proof of technology. There are natural ways to produce stability, including internal structure or shape effects. Spectroscopy would test composition. The European Southern Observatory, the Keck Observatory, and others would search for emission lines indicating outgassing. Water vapor, carbon monoxide, cyanides, and other comet signatures. A nearly featureless, sunlight-reflected spectrum could indicate a rocky or dark organic surface. Any deviations, say, unexpected absorption bands, would prompt further study, but still sit within natural possibilities until proven otherwise. Planetary radar, if geometry allowed, would be attempted. NASA's Goldstone Solar System radar has mapped asteroids and comets when conditions are right. A weak, specular echo, like a mirror-like return, would be intriguing because many natural surfaces scatter radio waves diffusely. Yet even specular hints are not a smoking gun. Smooth ice or layered structures can produce specular components. So far, we've learned the early steps. Fix the orbit, probe composition, and map rotation, all while resisting premature conclusions. Now imagine a further twist in our hypothesis. Sensitive radio telescopes, Green Bank, the Very Large Array, FAST, report a faint, narrowband tone co-moving with the object, slightly offset from 1,420 MHz, the hydrogen line. According to SETI best practice, multiple facilities would cross-check for radio frequency interference, apply on-target and off-target switching, confirm a Doppler drift that matches the object's motion, and attempt replication on separate days. Only if all those tests passed would the community cautiously use the phrase candidate signal. At that point, consensus would still demand restraint. Pulsars, Mossers, magnetospheric plasma, and spacecraft reflections all live in the radio sky. As NRAO engineers remind us, careful housekeeping, tracking satellites, cataloging transmitters, and working inside radio quiet zones is essential. A signal near the hydrogen line would be suspicious in the technical sense, worth attention, but not a conclusion. It would take weeks of independent verification, and many scientists would continue to search for natural causes. What if the signal began to show structure? In our scenario, it starts as a tone. Later, it shows simple modulation, prime numbers, then repeating sequences. According to decades of SETI literature, that is the kind of pattern people have proposed as a universal hello. Even then, mainstream practice would require blind analysis, independent pipelines, and strict statistical controls to avoid self-deception. Would that be enough to say, someone is answering? Not yet. It would be enough to justify the next step, a coordinated, pre-announced, carefully engineered reply. Chapter 4. A Whisper on the Hydrogen Line. This chapter previews how radio astronomers would interrogate any claimed signal and how they would minimize false positives before and during any attempted exchange. Radio astronomers are professionally skeptical. According to Breakthrough Listen's published methods, candidate detections undergo on and off pointing cycles, multi-beam checks, polarization analysis, and drift rate consistency tests. The aim is to distinguish a true sky-fixed source from local interference. If multiple telescopes on different continents report a co-moving tone with the same drift rate and the same sky position, the odds of a local culprit drop. In our hypothesis, the putative 3 ICE/ATLAS tone sits just off 1,420.4 megahertz, the neutral hydrogen spin flip line. Why would that matter? Cocconi and Morrison's original argument was that 1,420 megahertz is a universal standard. It's the most common element in the cosmos undergoing a simple quantum energy shift. A transmitter placed nearby, offset slightly to avoid the natural background, would be conspicuous to any radio astronomer. So far, we've learned that a hydrogen line adjacent tone is suspicious in the technical sense, but not yet conclusive. Suppose the signal shows a prime number pattern. The SETI Institute has long used primes as a hypothetical Rosetta Stone because primes are not easily produced by simple periodic physics. Even so, a rigorous team would pre-register hypotheses, committing in advance to which tests they will run. Then run Monte Carlo trials on synthetic data to assess how often random noise might mimic the pattern. They would do adversarial collaborations, one group arguing for noise, another for signal, both analyzing the same raw data. Only after such discipline would a responsible team alert the world. According to SETI's post-detection protocols, the discoverers notify international bodies, share data, and invite replication. The ITU might help protect the relevant bands from interference. COPUOS would likely convene informal consultations on transparency, avoiding hoaxes, and maintaining public calm. And the reply? Any response would be slow, simple, and mathematically grounded. The International Academy of Astronautics Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence encourages global consultation before transmitting. In practice, a reply would likely mirror the original. Primes, basic arithmetic, perhaps a binary representation of the hydrogen atom. Then a deliberate pause to see if the transmitter reacts in a way consistent with two-way exchange. If this imagined dialogue continued, if a change in the remote transmission consistently followed Earth signals by the predicted two-way light time, then the case for intentionality would strengthen. But mainstream consensus would still insist. Extraordinary evidence, replicated across facilities and instruments, before the word contact appears in a press conference. Chapter 5. Did they hear us? A careful reconstruction. This chapter previews how scientists would reconstruct Earth's radio history to ask a subtle question. If someone responded, when could they have known we were here? To test the reply idea, researchers would reconstruct the past century of Earth's radio brightness. According to open descriptions by the SETI Institute and NASA's Deep Space Network, our loudest signals are not sitcoms, but radars. Arecibo in its prime, Goldstone's X-band pulses, and other planetary radars that, when aimed at Venus or an asteroid, briefly outshone many natural radio sources nearby. By contrast, analog TV carriers and FM radio are weak at interstellar distances. Scientists could model when those brightest beams swept across different stars. They would convolve antenna patterns with Earth's rotation, pointing schedules, and the geometry of the sky. If a nearby star, say within a few dozen light years, fell repeatedly within the beam during our loudest years, it would have had a better chance to notice us. So far, we've learned that a proper "did they hear us" study is a geometry and power problem, not a mood or wish problem. Next comes travel time. Even at 10% of light speed, a speculative but often modeled interstellar cruise speed, years or decades would pass between hearing and arriving. If a hypothetical 3/8/ATLAS appeared in the mid-2020s, a reply to broadcasts story would imply eavesdropping in the late 20th century at the nearest plausible stars. Researchers would then test for "look elsewhere" bias, the human habit of seeing patterns in noise, by running the same analysis on scrambled data. If the reply timing still aligned better than chance after those controls, the idea would deserve further study, but still live under the label hypothesis. Meanwhile, skepticism remains essential. As astronomer Robert H. Gray and others have pointed out in discussions around the WOW signal and SETI methods, coincidences abound in large data sets. The only way to tame them is with pre-registered tests, blinding, and independent groups repeating the calculations. The right cliffhanger now is technical. If the arrival timing can be made to look plausible, what about the physical object itself? Does its shape, rotation, and heat behave like something built? Chapter 6. What is it made of? The engineering test. This chapter previews how shape, surface, and heat would be used to distinguish a natural fragment from a manufactured device. Shape is the first clue. Light curves tell you how an object spins and how elongated it might be. Oumuamua's brightness varied strongly, suggesting an extreme aspect ratio, longer than it was wide. That alone did not prove anything. Shattered fragments can be elongated. But if a hypothetical 3I/ATLAS displayed a rigid, slowly varying light curve with long-term stability, scientists would ask why. Does it have internal damping, or is it actively controlling its attitude? Thermal behavior is next. According to NASA's and ESA's mission reports, telescopes like Spitzer, Hubble, and the James Webb Space Telescope can probe how an object absorbs and emits heat. A natural body warms and cools with distance from the sun, roughly as the inverse square of illumination, modulated by rotation and material properties. If an object's temperature plateaued or showed signatures of active heat management, like surfaces that change emissivity with angle, that would be unusual. There are natural explanations. Porous materials, fluffy regolith, or complex shapes can create odd thermal curves. Still, a stable, selective thermal response across wide wavelength ranges would ask for an explanation. So far, we've learned that odd shapes and heat curves raise eyebrows, but do not yet close the case. Radar echoes would probe surface smoothness at the radio wavelength. Specular returns, mirror-like glints, suggest flat or gently curved facets oriented just so. Natural ices and layered deposits can give partial specular reflections, but a set of repeating angular flashes, synchronized with rotation, would be provocative. Spectroscopy would search for outgassing lines. A faint coma near perihelion would suggest volatiles, like 2I/Borisov. No coma could mean a rock, a devolatilized comet, or a surface crust sealing the interior. Unusual absorption features might hint at complex organics, exotic ices, or even thin metallic films. Materials scientists would caution that many laboratory-made films and many meteorite phases produce similar signatures. Matching a spectrum to manufactured requires knowing the natural catalog first. If, after months of observation, the balance of evidence still leaned toward an engineered interpretation, the community would push for the next test. A carefully designed, globally agreed, non-invasive exchange. Chapter 7. Talking Back. Protocols and Precautions. This chapter previews how a first reply would be structured, how global organizations might coordinate, and what ethical guardrails would apply. The conservative endpoint of decades of SETI workshops is simple. Respond slowly, clearly, and only with information we are already comfortable broadcasting. According to the International Academy of Astronautics principles, discoverers should share data openly, consult widely, and avoid unilateral action. The ITU would help protect receiving bands from interference during the attempt. COPUOS members and observers would encourage transparency and record-keeping for history. A reply would likely begin with a short mathematical sequence, primes or simple binary arithmetic, so the receiver can confirm that two-way exchange is happening. Then, if that is acknowledged by a predictable change on the other end, a second, slightly richer packet might follow. Definitions for units derived from physical constants, for example using the hydrogen line period as a time unit and the wavelength as a length unit. The entire exchange would be designed to survive noise, heavy error correction, bursts separated by pauses, and explicit markers for the start and end of each frame. So far, we've learned that any first reply would be mathematically minimalist and globally consulted. Ethics matter. COSPAR's planetary protection guidelines focus on biological contamination for missions to places like Mars or Europa. While they don't address interstellar diplomacy, the principle of avoid harm remains. Powerful Earth transmitters should not endanger wildlife or aviation. If the imagined object broadcasts while near Earth's orbit, terrestrial authorities would coordinate so our reply windows avoid interference with critical systems. And on the content side, the safest rule is to reveal nothing about our vulnerabilities beyond what we already project every day. If a second exchange follows, if a repeated two-way light time pattern builds a cadence, scientists would ask whether the content starts to teach rather than merely greet. And if it did, what would we do with that? Chapter 8. Earth Reacts. Mind, Markets, Meaning. This chapter previews the social and psychological ripples that even a cautious, well-verified exchange would produce. A genuine two-way mathematical exchange, verified by independent observatories, would be a global event based on how people reacted to the Apollo landings, the first images from Hubble, and major exoplanet announcements. We can guess at some patterns. Curiosity would surge. Observatories would host late-night listening sessions, universities would see enrollment bumps in physics, engineering, and computer science. Public broadcasters would produce explainers, and science channels would run calm nightly updates. Psychologists would also prepare. The Stanford Overview Effect research into astronauts' mental shifts suggests that contact could expand people's sense of identity from national to planetary. Sleep might be uneasy for a while. not from fear, but from awe. Faith traditions would engage with the news within their theologies. The Vatican's astronomers have long said that discovery of life elsewhere need not contradict Catholic doctrine. Islamic scholars have noted the Quran's openness about creation beyond Earth. Buddhist teachers often speak about consciousness as a universal property. These are nuanced conversations, and they would continue with respect. So far, we've learned that society can hold wonder and caution at the same time, and that a careful presentation of facts helps. Markets respond to uncertainty. As history shows around major space milestones, aerospace stocks can swing. But the enduring shift is cultural, a longer planning horizon. Urban planners might consider dark sky policies. Schools might expand astronomy clubs. Amateur radio and telescope communities would welcome new members, and the public would become more literate about spectrum, interference, and why radio quiet zones exist. At a quieter personal level, people might look up more often. That habit alone changes how nights feel. And as attention shifts from "did it happen?" to "what does it mean?" a practical question appears. Should we build anything new? Either to meet a visitor or to join a larger network? Chapter 9. Building carefully. Missions, beacons, and law. This chapter previews what a rapid mission might look like in principle, what a beacon would require, and which legal frameworks would need updating. If a future object lingered within instrument range, mission designers would explore flyby concepts. According to NASA's and ESA's archives, rapid, fast flyby architectures rely on existing heavy launchers, solar electric propulsion stages, autonomous navigation, and distributed small probes. A sensible, conservative payload would prioritize remote sensing, optical, infrared, radio, over any contact hardware. The aim would be to maximize science while minimizing risk and ambiguity. The James Webb Space Telescope and upcoming large ground-based telescopes could support such efforts with spectroscopy and thermal mapping if tracking limits allow. A beacon is different. It implies we intend to join a broader network. Technically, as engineers at JPL and ESA would remind us, this requires coherence. Thousands of distributed elements acting like one, with nanosecond timing anchored to atomic clocks. Power demands can be large. Environmental impacts must be managed, and governance is essential. The Outer Space Treaty, the Liability Convention, and ITU regulations would need interpretation for a brand new kind of infrastructure. So far, we've learned that missions can be fast, but must be safe, and beacons are possible in principle, but come with weighty responsibilities. 3 pathways would likely be discussed. The conservative path. Strengthen listening. Do not transmit beyond what we already leak. The participatory path. Build capability, but switch it on gradually under international oversight. The ambitious path. Join fully and quickly. Each has trade-offs. The middle path. Capability with controls, often attracts broad support because it keeps options open while we learn. Whichever path we take, law and ethics will need to keep pace. Who speaks for Earth? How are messages ratified? How do we ensure transparency and archive everything for posterity? These are solvable problems if we prepare before emotions run too high. And if a message ever went beyond math, if it contained engineering hints, how would we analyze it without fooling ourselves? Chapter 10. The Knife Edge. Proof without illusion. This chapter previews the scientific guardrails that keep wonder honest: blinding, pre-registration, independent replication, and humility. Extraordinary claims require extraordinary evidence. That phrase, popularized by Carl Sagan, is not a poetic gate, it is a checklist. In practice, teams pre-register their analysis plans so they can't unconsciously tune parameters until a signal appears. They blind themselves to key labels. They create adversarial collaborations, where skeptics and proponents analyze the same data independently and then meet in the middle. They run null tests, injecting fake signals to ensure their pipelines don't trigger on artifacts. So far, we've learned that method is our best defense against wishful thinking. In our hypothesis, if a series of narrowband transmissions co-moving with an interstellar object showed prime sequences, two-way cadence consistent with light time, and content that survived independent decoding by multiple groups following pre-registered methods, then the word contact would be discussable in serious circles. But even then, claims would be bounded. We would say what we know, a narrowband source at X showing Y pattern at Z confidence, and what we do not. We have not yet identified mechanism A, ruled out natural process B, or tested explanation C. The lesson from 1I/Oumuamua is instructive. According to mainstream analyses published in major journals, small, non-gravitational accelerations can have natural origins, even when visual coma are absent. Alternative ideas, light sails and exotic ices, are part of the literature, but they remain minority views. The community corrected itself through data and debate, not rhetoric. Humility is not the enemy of wonder. It is wonder's guardian. It is how we avoid seeing canals on Mars again, while remaining open to canals if they are truly there. Chapter 11. If the message teaches. This chapter previews a practical thought experiment. If content ever rose above greeting, if it resembled an instruction manual, what then? Suppose, purely as a hypothesis, that future transmissions contained layered content, math headers, physical constants, then rough engineering specifications that our century could actually build. Information theorists would first analyze the coding, error correction, framing, symbol rates, redundancy. If it checked out, engineers would still proceed cautiously, simulating what they had received, verifying that it is internally consistent and physically plausible. So far, we've learned that even if content appears helpful, engineering discipline still applies. Next come ethics and governance. The UN's space law framework would need a communication governance annex. Sharing would be default. Secrecy would be corrosive. Education would expand, not just graduate programs, but community courses, explaining spectrum basics so citizens can follow decisions. Environmental safeguards would be mandatory. Ground arrays sited away from migratory pathways. Radio quiet reserves expanded. Lunar farside considered for the most sensitive receivers. At the center is a deeper question. Do we build or do we watch? That choice goes to identity. Are we explorers right now, or do we let our grandchildren decide? There is no single correct answer. There is only a commitment to make the decision, whatever it is, carefully, transparently, and with an eye to stewardship. Chapter 12. After the Echo. This chapter previews a calm landing, what it means to live with the possibility that we are not alone, and how to rest inside that knowledge. Even without a third confirmed eye object, even without a verified exchange, the very exercise changes our posture toward the sky. We remember that the solar system is not fenced. Material drifts between stars, objects pass through. Signals can too. We balance caution with curiosity. We let the night be big. So far, we've learned that wonder does not require certainty. It only asks for honesty. If a 3I/ATLAS ever appears in the literature, it will be studied with the tools that brought us here. Surveys scanning the sky, radio telescopes guarding their bands, mission designers ready to move, philosophers and faith leaders ready to listen, and a public capable of holding awe and skepticism in the same breath. Until then, the mature answer to the title question, did we summon 3I/ATLAS, is this. Not yet, not that we can say, and certainly not in any confirmed way. The mainstream consensus is that 1I and 2I were natural. Any future 3I/ATLAS would have to clear a high bar, multiple independent lines of evidence, replicated and transparent, before science would change its mind. And if that day ever comes and something answers, we'll meet it with patience, clarity, and care. For tonight, let the quiet be enough. Somewhere, hydrogen atoms flip their spins and whisper their perfect 1,420 megahertz tick into the dark. We listen, we learn, and we wait, not idly, but attentively, for whatever the universe decides to say next. What would that first unmistakable sentence from the stars actually sound like? And when it arrives, will we recognize our own reflection in the way we choose to answer?